Before we get started, I need you to take the freezing point and melting point graphs that correspond to this information and draw in the curve that goes best with the plotted points that are already on those graphs. Once you have done that, I need you to take 8 to 10 minutes to answer the questions on the front side of the goldenrod sheet that goes along with those graphs. When you've done that to the best of your ability, go ahead and push play and we'll go through those answers pretty quickly. Let's start by drawing in the plot for the freezing curve. You can see I do not connect the dots. I just draw a line that fits the data pretty well instead of connecting all the dots. When we plot the graph, we can clearly see that this graph has two plateaus. We have an upper plateau and a lower plateau here. Well, the upper plateau actually represents the freezing point of the substance. Right here we have the liquid cooling, and when it gets cold enough it starts to freeze and turn into a solid. Well, until it turns into a solid, the temperature remains constant. Once it turns into a solid, it continues to cool down. So we can get the freezing point temperature based on that first plateau, and it appears to be at about 62 degrees Celsius, but of course there's some leeway there, so that's why I got plus or minus 2 degrees Celsius. So then the question is, what does this lower plateau signify? So you really got to think about what a plateau can tell you.
Many a hand has scaled the grand old face of the plateau. Nothing on the top but a bucket and a mop and an illustrated book about birds. You see a lot up there, but don't be scared. Who needs Jackson when you got words?
All right, very wise words there from Mr. Kurt Cobain. Plateaus can be puzzling, but this plateau, if you think about what we did in the lab, could represent the temperature of the ice bath. We had the solid in an ice bath. Well, once the solid gets to the temperature of the ice bath, the temperature is going to level out again. So that last plateau represents room temperature, or the temperature of the ice bath in the case that we did in the lab. So we can draw in the melting point data as well, and once again I would draw a best fit line and not connect those dots dot to dot. And then the question is, what the heck is that thing right there? That's some data that doesn't fit into our graph. Well, it seems a little erroneous. We call that erroneous data an outlier, and it can probably be ignored based on all the other data that was collected. That seems to be pretty reasonable. So something happened here where we got a bad reading on our data. Well, this graph has one plateau. Now we have represented here the melting point. So this is the solid warming up, and then as the solid melts, the temperature levels out again. And once it's all melted into a liquid, the liquid temperature increases. So the plateau in this case represents the melting point, and once again it appears to be at about 62 degrees plus or minus 2 degrees depending on how you read that. And just like I said, that plateau represents the melting point. Let's try to identify what this unknown substance is. Well, the melting point of this substance was, like we said, 62 plus or minus 2 degrees Celsius. Now, the freezing point was also 62 plus or minus 2 degrees Celsius. That is not information that is new to you. You know that, you probably just never realized it before. We know by living in Nebraska that the winter times we're really aware of a certain temperature, 32 degrees Fahrenheit. Ice forms below 32 degrees Fahrenheit, and the ice melts above 32 degrees Fahrenheit. At 32 degrees, it's equally likely for the water to be in the solid phase or the liquid phase. It is the melting point slash freezing point of water. They're the same thing. Now we got to use the table at the end of the experiment to find the substances that are in this melting point range. So if you looked at that table, you should have picked out 3-chloro-2-butanoic acid, malic anhydride, and palmitic acid. Those are the organic substances that were in our temperature range. So one of those three solids is represented by the data on these sample graphs. So how can we determine which organic substance it is? Well, if you look at the table there was other physical data that you could use. So the best thing to do would be to do another test, so you can tell which of the three substances it actually is. The physical properties that are remaining that haven't been tested include density, boiling point, and then solubility in water, benzene, and alcohol. Which test would be the best? So I've taken the table here and just focused in on the three that we're looking at. If you look here first at solubility in alcohol, you can see this would not be a good test to do because all three substances are soluble in alcohol. So we wouldn't be able to tell which one is which. So if we look at solubility in benzene, we come across a problem because the solubility of 3-chloro-2-butanoic acid is unknown in benzene. We can't really get a definite answer because we don't know what that substance will do in benzene. The same story is going to happen with water. We don't know what 3-chloro-2-butanoic acid does in water as far as solubility or not, so that's not a good test to do. Let's look at boiling point. Maybe boiling point's a good test. Well, if you get lucky and palmitic acid is the unknown, you'll be able to tell right away because it's got a significantly higher boiling point. But malic anhydride and our 3-chloro-2-butanoic acid have very similar boiling points again. So this is not a good definitive test for what that substance is. So of course, the best test would be to test the substance's density. If you have precise lab equipment, it's pretty easy to tell the difference between these densities in the lab. So that would be the best test to do to find out exactly what that unknown substance is. Right now I'm going to start a demo that we'll explain here in a second, but what I'm going to do is take some solid iodine and put it in a beaker. Put the beaker on a hot plate and heat that iodine up. In a little bit we'll come back to this demonstration and see what is going on with the iodine. While that's going, let's talk about phase changes. When matter changes state, that's called a phase change. So we should know most of these phase changes. A couple of them might sound new to you. Solid going to a liquid, otherwise represented by the little symbols S and L. In order for a solid to turn into a liquid, you have to put some energy in, and of course that is called melting. You can see the ice melting there. The only way the ice melts is if you put energy into the ice. The opposite of melting is a liquid turning into a solid. In order for that to happen, you have to remove energy from the liquid. If that occurs, that is freezing. So the formation of ice from liquid water is a good example there. Liquid going to a gas, boiling some water on the stove. You have to put energy in to get it to boil, to turn into water vapor or steam. That is called boiling, of course. The opposite of that, removing energy from a gas to make it turn into a liquid, is called condensation. The best example of condensation is dew in the summertime. The very humid summer air is packed with water, and in the cool evenings, that water vapor comes in contact with that cool grass and causes the water vapor to condense into a liquid, and that's what forms the dew on the grass in the morning. The next two phase changes may be unfamiliar to you. It is possible for a solid to turn directly into a gas, and that's kind of what you see going on here with the iodine demonstration. But when a solid turns to a gas, that has a specific name, and if you can't think of it, maybe this will help you out a little bit.
Early in the morning, rising to the street, light me up that cigarette, I'll strap shoes on my feet. Got to find the reason things went wrong. Got to find the reason why my money's all gone.
In case you are totally oblivious to music, that is the band Sublime. A solid turning to a gas is called sublimation. The opposite of that is a gas turning into a solid when energy is removed, and we call that deposition. Hopefully now we can go back to our iodine demo and I can show you an example of sublimation and deposition. You can see inside the beaker it looks like we have a purple cloud, or maybe even a it's a purple haze, and that purple haze is caused by the sublimation of the iodine. The iodine is heated up and it turns directly into a gas. It skips the liquid phase. Does anybody know what comes from a purple haze? If not, maybe this will help you.
I never meant to call you when you sorrow. I never meant to cause you any pain. I only wanted to see you laughing in the purple rain. Purple rain, purple rain.
Of course, a purple rain comes from a purple haze. Okay, enough with the little jokes. The other phase change that we see with this demonstration is deposition. The iodine gas comes into contact with this porcelain cup here at the top that has some ice water in it. It's a very cool porcelain cup, and that iodine gas loses energy and deposits onto the bottom of the crucible, as you can see here with these pretty purple crystals. Now, just a little side note that really has nothing to do with heating and cooling curves, but iodine belongs to a group of substances that exist in nature as diatomic molecules. Whenever iodine is found in nature, it exists as I2, two iodine atoms bonded together. That's where the word diatomic comes from, two atoms. The same is true for hydrogen, oxygen, fluorine, bromine, nitrogen, and chlorine. These atoms only exist in nature as diatomic molecules. So you might think, how will I ever remember this? In physics, you should have had a physics friend to help you remember the colors of the visible light spectrum. It was Roy G. Biv. Red, orange, yellow, green, blue, indigo, violet. Your friend was Roy G. Biv. Well, in chemistry, your friend is Hofbrinkel. He's going to help you remember the diatomic molecules. Okay, hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine only exist in nature as diatomics. Another way you could possibly remember it, the atoms form a L shape on the periodic table. Hydrogen is over here, but the rest of them are right here. Nitrogen, oxygen, fluorine, chlorine, bromine, iodine. They form this little L, this little part of the periodic table right here. The only one that's kind of out of that L is hydrogen up here. You need to know the atoms that exist as diatomic molecules. You can remember that by remembering your chemistry friend Hofbrinkel.